In this video, we're going to look at the different types of reactions that exist, how you can identify the type, and then how you can actually use that to predict the products that will form. All right, so you'll be able to look at the reactants and know exactly which products will form and then balance it. So essentially, you'd be writing an entire reaction. Okay, so there's actually, millions of reactions, but there's only, so many categories that exist. We're going to look at 5 specific reaction types here. And you'll see that the names kind of key you in on what happens. So we'll go through each one. We'll look at some examples. All right, but you can see them listed here. We'll do synthesis, decomposition, single replacement, double replacement, and then everybody's favorite, combustion. All right, so we'll start just going through them one at a time. So the first type we're going to look at here is a synthesis reaction, also known as a combination reaction. Understanding the definition of these reactions is important because it basically keys you in on what takes place. So in a synthesis reaction, two elements here are going to combine to make one compound. So if you look at the generic kind of equation here, you have an element reacting with an element to form a compound. It's very important to understand that when you're looking at all these different reactions that we're going to look at today, all the different types, it's the reactants that tell you which type of reaction is going to happen. Okay, because many times the products won't even be listed. So by analyzing the reactants and seeing that it's an element plus an element, that tells you immediately that it's going to be a synthesis and they're going to come together to form a compound. So a nice little real world example of this, you take kind of a shoe, put some wheels on it, you ended up with some roller skates there or some Heelys. So that would be a synthesis reaction. A good real world example of a synthesis reaction is rusting. Iron reacts with oxygen in the air to form iron 3 oxide. It's a chemical reaction taking place. You're getting new substances. So if we wanted to write this out, okay, iron would just be the element Fe, all right, reacting with oxygen. Remember, oxygen is a diatomic, so it'd be O2, okay, and it's going to produce iron 3 oxide. So you got to be careful here. How are you going to get the formula for iron 3 oxide? It's an ionic compound, so you're going to have to do symbols, charges, crisscross. All right, so you might need to do this off to the side. So iron is going to be Fe, oxide is just O, so those are the symbols. The charge on the iron is right here in parentheses, it's 3. Oxygen, when you look it up on the table, is 2. All right, 2 minus. So when you crisscross, the formula here for iron 3 oxide is going to be Fe2O3. Okay, so that's the reaction that's taking place when rusting occurs here. But the last thing you got to do here is balance it. So I showed you how to do this using reactants products tables, which you're more than welcome to keep using, but you can balance just by kind of looking at both sides of the equation here and just keep going back and forth until you make the elements kind of match up. So I'll show you how to do that here. So for example, the first thing I do is I look for something that is different on each side. So in this reaction, I can see that I have 1 Fe on the left, but I have 2 on the right. So I'm going to fix that. I'm going to put a 2 in front of the Fe, okay? But then I notice I have 3 oxygen here on the right and only 2 over here. Well, the only way that that's ever going to work is if I get the oxygen on the left and the right to be 6, okay? 2 and 3 are never going to match up unless I get it to be 6. So by putting a 3 in front of the O2, that gets me 6 on the left, and then by putting a 2 in front here, that gets me 6 on the right. But what happens is this messed up my iron. I now have 4 iron on the right, so I have to go now and fix my iron here on the left, and that's going to end up having to become 4, okay? But once I do that, now this is balanced, and I didn't need to use a reactants products table. And the beautiful part about this is you can always check your work, all right? You can always make sure before moving on that you got this right. Check, say, okay, I have 4 Fe on the left, 2 times 2, I have 4 Fe on the right. I have 6 oxygen, 3 times 2 on the left, 2 times 3 oxygen here on the right is 6. So everything matches up. That would be that equation, and it's balanced now. And you didn't have to use the reactants products table. So let's do a real example here. All right, typically this is how you're going to see reactions from now on. All right, all you're going to get is the reactants here. And you have to predict what would form, identify the type, and then do the balancing, okay? Notice here, it doesn't say, what type of reaction is taking place. You have to analyze it and know the type in order to be able to predict the products here correctly, all right? So the first thing you do for any of these reactions, always, you analyze the reactants because the reactants will tell you what type it's gonna be. So if I look here at my reactants, the first thing I see is Mg, all right? Well, Mg is just an element, okay? And I literally label these things. So Mg is an element, all right? N2. N2 is actually a compound, okay, but we treat it like an element because it's a diatomic. He can't be by himself. He can't just be N. So we treat that as an element. So this would be the definition of a synthesis. We have an element reacting with an element. So we know that a compound needs to form, okay? So the first thing you need to be careful of here is you can't just say, oh, a compound's going to form and smush them together. You can't just write MgN2 because that's not right. You're not following the proper rules here, all right? Mg and N are going to come together to form an ionic compound, okay? So in order to get an ionic compound, you have to do symbols, charges, crisscross. You can't just smush them together, all right? So in order to do this correctly, I have to do symbols, charges, crisscross because an ionic compound is forming. So yeah, you might need to write this off to the side. So I know Mg is coming together with N. The charge of Mg when I look it up on the table is 2 plus. Nitrogen when you look it up on your table is 3 minus. All right, so when you crisscross, the compound that forms is Mg3N2. Okay, so you got it. This is something you just got to pay attention to. If you are forming an ionic compound in any of these reactions, you need to do symbols, charges, crisscross. Okay, don't just, smush them together or whatever. All right, so that's the actual product that forms in this reaction. And remember, you needed to realize that this was a synthesis in order to do this. By analyzing the reactants, knowing they were both elements, that told you it was synthesis, which told you what to do here to bring both elements together and form a compound. The last thing you have to do here is balance it. So when I look for some differences, I see that I have 3 Mg on the right side. So now I have 3 Mg on the left. I have 2N here on the left, and I have 2N on the right. So all my elements match up. I'm done. It's balanced. Okay? So you need to be able to take reactants like this, predict the product, know the type, and then balance it. So this is a good example of a synthesis reaction. If you take magnesium metal, okay, and react it with the oxygen in the air, and you kind of, put it in the flame, it, gives off the bright color. You might remember seeing the bright white light in the lab earlier in the year, and it forms magnesium oxide. It's actually a synthesis reaction taking place. It's just that the magnesium oxide kind of turns whitish and kind of falls away, and you don't really see it. So the next type of reaction we're going to look at is a decomposition reaction. It's kind of the reverse of a synthesis, all right? This is when you have a compound breaking down into its elements, all right? So if you look at the general reaction here, you have some form of compound, all right, and then it splits apart into its individual substances or individual elements, all right? So this is a good example. You have this guy sitting here flirting with his girlfriend. He says something inappropriate, and pretty soon, he no longer has his girlfriend, all right? So this is a good example of a decomposition reaction. We saw an example of a decomposition reaction earlier in the year, all right? If you remember when we took sugar and we added some sulfuric acid to it, it started to, all right, form that dark black, solid substance. We were actually decomposing the sugar, all right? We were breaking it down into its individual parts, the carbon, the hydrogen, oxygen, so on, all right? So that was a good example of a decomposition reaction where you take one compound and you split it into its parts, okay? That's kind of the important part here for a decomposition reaction. You're starting with a compound in your reactants. That's the dead giveaway that it's decomp. So now we're ready to try an example here. Again, all you're typically going to be given here are the reactants, and you got to predict it all. You got to know the type, you got to balance it, predict what forms, all right? So the first thing I do for any of these reactions, you always analyze the reactants, okay? Figure out if you're dealing with elements, compounds, whatever. So when I analyze the reactants here, NaCl, well, that's a compound, right? So if the only reactant you have is a compound, boom, you immediately know that's got to be a decomposition reaction. I have to separate the compound into its parts. you literally just rip it apart into the elements that are there. Okay, so NaCl is going to split apart into Na plus Cl. But the last thing you do here, okay, so you immediately split apart the compound into its individual elements. The last thing you do is ask yourself this question for each element. Is it a diatomic? If it's yes, you put the 2. If it's not, you leave it as it is. So sodium is not diatomic, so it just stays as Na. Chlorine is diatomic, so it needs the 2. When you do one of these decomp reactions and you rip apart the elements in your products are either going to have a 1 or a 2 with them as their subscript. Okay, no matter the numbers that are over here, that's the only possible option. You can't just rip something apart and put the numbers, like for example, if you had AlCl3, you can't just rip it apart into Al plus Cl3. That's not how it works. There's no such thing as a triatomic, okay? So be careful of that. You rip apart the compound into its elements and then ask yourself, is the element diatomic? If it is, put a 2. If it's not, you just leave it as the element. All right, so the last thing we need to do here is balance this. I can see that I have 2 chlorine on the right side, so I need 2 chlorine on the left, so I'll put a 2 in front, okay? And now I have 2 Na on the left, so I'll put a 2 in front, and now everything should work. If you check your elements, I have 2 Na on the left, 2 Na on the right, 2 Cl on the left, 2 Cl on the right. Okay, so this would be your overall balanced equation. This is a good example of a decomposition reaction. If you take mercury 2 oxide here and you heat it, it will actually separate into mercury and oxygen. So the oxygen would just kind of evaporate away and you'd be left with pure mercury in the test tube. All right, we know that mercury is very dangerous, so we would not want to do this, but that's a good example of a decomp reaction. So the next type of reaction we're going to look at is a single replacement reaction. It's just like it sounds. One thing is going to replace another. So an element is going to replace another element in a compound here. All right. So in a single replacement reaction, here's the general form of it. All right. Remember, you always analyze the reactants. The reactants tell you what type of reaction it's going to be. In a single replacement reaction, you have an element reacting with a compound. Okay. And then what happens is the lone element kicks someone out of the compound and the lone element jumps in that spot. Okay, so this is a single replacement reaction. One thing replaces another. And just kind of a little reminder here, metals can only replace metals. All right, so if the lone element is a metal, he could only possibly kick out the metal in the compound. If the lone element here is a non-metal, he could only possibly kick the non-metal out of the compound. So that's something very important to pay attention to. Once you realize it's an element plus a compound single replacement, you need to analyze the element and figure out if it's a metal or non-metal. Okay, so a good example of this you can see here. All right, this guy in his orange shirt, all right, comes over to this couple, and pretty soon the girl is now dancing with the guy in the orange shirt, and the other guy is off by himself. Okay, so that's a good example of a single replacement reaction. It's very important to note here that sometimes these reactions don't actually work. They might not happen. All right, the only way this works is if the lone element is more reactive than the substance he's trying to kick out. Okay, so that's very important. We'll have to analyze this a little bit further. So anytime you see a single replacement reaction, you need to always remember, okay, I need to make sure it actually happens first. So in order to see if a single replacement reaction happens, you need to analyze something called the activity series. All right, good news is you would never need to memorize this. You would always be given an activity series or have an activity series available to you when you're doing these reactions. You just have to remember to use it, okay? You would only use the activity series for single replacement reactions. That's very important to remember. You would only do this, only look at this if you're doing a single replacement. Okay, so the basic gist here is any metal that's higher up on the list can replace any metal that's lower. Otherwise, no reaction would occur. Okay, so if you notice here, lithium's at the top. All right, he could kick out any other metal. Whereas something like silver is not very reactive. He's not going to be able to kick out anybody on this list. Okay, something else to pay attention to. It says over here, metals from lithium to sodium can replace hydrogen from acids and water. So if you have here any metal from lithium to sodium, these guys right here, they're strong enough to kick hydrogen out of water and acids. So if you notice, hydrogen is on this list. Hydrogen is not a metal, but hydrogen acts like a metal. He forms that 1 plus charge, okay? So if you were to see hydrogen here acting like a metal in a compound, all right, any of these elements from lithium down to lead can kick hydrogen, okay, out of acids, all right? But only lithium to sodium are strong enough to kick hydrogen out of water. And it kind of makes sense. Like you're not going to see your aluminum can, blowing up and reacting with soda when you put it in the can, okay? Only some of the elements react with water. So that's just another thing you need to watch out for, okay? But anytime you have a metal that's higher on the list, it would kick out a metal that's lower, all right? If you didn't have that happening, if you had a lower metal trying to kick out a higher metal, no reaction would actually take place. So you always need to remember to look at the activity series for single replacement reactions. So this is just a bigger list. You can see there's more elements here, but the same rules apply. Anybody who's higher on the list can kick out anybody who is lower. So if you notice there, gold is very low, not very reactive. That's why it's very useful in jewelry. So we saw the activity series for metals, which you would always be given. Here's the activity series for non-metals. And you would never be given this list because it's right from your periodic table. All right. So if you were, doing a single replacement reaction and the lone element was a non-metal, non-metals can only kick out non-metals. So you would look at your halogens essentially. You would look at your periodic table. Higher halogens can kick out anybody who's lower. So fluorine on your periodic table is at the top of the halogens. He can kick out any other element, all right? But iodine is at the bottom of the halogens. He's not able to kick out any other halogen, all right? So just important to remember that non-metals, do experience this activity series, but you're not given a separate list. You use the table for it, all right? The only way this works is if the higher element, okay, kicks out anybody who is lower. Otherwise, it's no reaction. So a good example of this would be anytime you take a metal and you react it with acid, typically the metal is able to kick out the hydrogen, forming hydrogen gas. Okay, you'll see a lot of bubbles taking place. But remember, not every metal would be able to do this. It has to be higher on the list than hydrogen in order for this to be able to occur. So anytime you see single replacement, you need to remember to look at the list. All right, so let's try this example here. All right, so I have Zn plus HCl. Remember, you always have to analyze the reactants first. All right, figure out if they're an element, compound, whatever. So the first thing I see is Zn. That's just an element, so I like to label it. HCl, well, that's going to be a compound. So element plus compound is the definition of single replacement. Anytime you have an element reacting with a compound in your reactants, that's single replacement. Okay, so remember, once you know it's single replacement, you have to analyze your lone element and figure out, is that a metal or non-metal? Okay, so in this case, zinc is a metal. So he could possibly kick out the metal in the compound. Metals kick out metals, non-metals kick out non-metals. So because the lone element is a metal, he could possibly kick out the metal from the compound. So remember, metals are always written first. So zinc is going to try to kick out the hydrogen, but this only works, okay, because this is single replacement. This only works if zinc is higher on the list than hydrogen. So if you go back to that activity series and look, zinc is higher on the list than hydrogen. So you immediately know that zinc gives hydrogen the boot. Okay, hydrogen's getting kicked out. So one of your products here is going to be hydrogen, but it's diatomic, so it's going to be H2. All right, but then there's going to be a second product here. All right, zinc is going to jump in his spot. Okay, so it's kind of like you want to think like hydrogen's getting kicked out, but then zinc is jumping in with the Cl. But you're forming a compound. You're forming an ionic compound, a metal and a non-metal. So you have to do symbols, charges, crisscross. You can't just take the Zn and smush it together with the Cl. You have to follow the rules. So when you do this, you have Zn coming together with Cl. So you got to do the charges now. Zinc is always 2 plus. Chlorine, when you look it up on the table, is minus. So when you crisscross, the actual formula is going to be ZnCl2 of the compound that forms. So anytime you're forming ionic, you need to do symbols, charges, crisscross. Okay, so those are the two products that form here. The last thing I need to do is balance this. I see 2 hydrogen on the right, so I need to put a 2 in front here. Well, that gives me 2 Cl now on the left. Well, if you look, I have 2 Cl now on the right. I have 1 Zn on the right and 1 Zn on the left. I'm balanced. Okay, remember, always important, check each element. Make sure that you are making them balance. Okay, so anytime you have an element plus a compound, it's going to be single replacement. As soon as you know it's single replacement, analyze the lone element, figure out if it's a metal or non-metal so you know who he could possibly kick out, and then you got to check the list. All right, so we're going to try another one here. I can give you a moment. If you want to try this on your own, pause the video, see what you come up with. All right, so when we do this one, same deal. You always analyze the reactants. All right, I have copper, which is an element, FeO, which is a compound. Element plus compound is single replacement. All right, get used to writing the type nearby. It's very helpful because you need to remember, even if it doesn't ask you to identify the type, you need to figure out what type of reaction it is in order to predict the products correctly here. All right, so because this is single replacement, I need to analyze the lone element. All right, is it a metal or non-metal? Well, copper is a metal. Okay, so he could only possibly kick out the metal from the compound. All right, so metals kick out metals. Metals are always written first. So copper could possibly kick out iron here. But remember, it's single replacement. So this would only happen if copper is higher on the list than iron. Okay, so you need to remember, single replacement, check the list. When you check the list for this one, copper is not higher on the list than iron. Copper cannot kick out iron. So this is no reaction. All right, RXN just stands for reaction. So you would not write the products that form because there's no reaction that takes place. If you took copper and put it here in this iron 2 oxide and just mix them together, nothing would take place. All right, so remember, for your single replacement reactions, you need to check your list. So this is a good example of a single replacement reaction. If you took a piece of potassium metal and you put it in water, remember potassium is one of those alkali metals that will react pretty violently here with water. You actually form potassium hydroxide and H2 hydrogen gas. Okay, so the potassium is high enough on the list that he can kick the hydrogen out of water. Only some elements can kick hydrogen out of water. So the fourth example we're going to do is double replacement reaction. It's similar to single replacement, except it's double. Two things are going to switch spots. Okay, so it's kind of going to be like a swap here. All right, so if you look at this, remember, always analyze the reactants here. The reactants will tell you which type of reaction it's going to be. All right, so when we look at this, for a double replacement, you always have a compound reacting with a compound. Okay, and then literally what I like to do is I like to say, okay, the metals are going to stay where they're at, and then the non-metals switch spots. Okay, you could easily leave the non-metals where they are and switch the metals, but that's kind of how I like to think about it. The metals stay where they're at, and then the non-metals switch. That would be a double replacement reaction. And just remember here, the metals are always written first in the compounds, right? Sometimes these don't happen either, okay? The way you know if they happen is if a precipitate forms, but for this unit, we're just going to assume that all double replacement reactions happen, right? When we do solutions and then we look at solubility rules, that's when we'll worry about if a double replacement reaction happens or not. But for this particular part, we're just assuming that all double replacement reactions happen, okay? So it's not like single replacement. You don't look at the list. You only look at the list for single replacement. For double replacement, they're going to happen. Two things are going to switch spots. So as I said, a lot of double replacement reactions involve the formation of a precipitate. So typically you would mix two aqueous solutions or two solutions made with water. When you mix them together, you get that precipitate or that solid forming. But again, For our purposes for this unit, all double replacement reactions are going to happen. So let's do an example of this one. All right, remember for any of these reactions where you got to predict products, always analyze the reactants. Okay, so when I look at the first substance here, NaOH, that's a compound. All right, FeCl3, that's a compound. So compound plus compound is a double replacement reaction. Okay, so get used to writing that nearby. It's always good to make sure you're identifying the type, even if they don't ask you, because then you know exactly what's going to take place. All right. So we don't check any list. That's only single replacement. Double replacement happen. Okay. So like we said, I like to leave the metals where they're at and switch the non-metals here because that would be a double replacement. Two things are switching spots. All right. But the key here to remember is you're going to form two new compounds. And these are typically going to be ionic compounds that are forming. So you're going to need to do symbols, charges, crisscross here for the products. Okay. So when you're forming your products here, the first product I'm going to get, and I'm going to write it down here. I know that I'm going to have sodium. All right. And his new friend is going to be the Cl from the FeCl3. Remember, we're keeping the metals and we're switching the non-metals here. But in order to get the actual formula, I need to do symbols, charges, crisscross. So sodium's going to be plus. Chlorine, when you look him up on the table, he's in the 1 minus column. When you crisscross, it's just NaCl. Okay, so that's your first product that forms. And then the second product, remember the Fe is staying where he's at, and he's going to get a new friend. All right, his new friend is going to be the minus part, or the OH, from the NaOH. Okay, so you still need to do symbols, charges, crisscross. Anytime you're forming ionic compound, symbols, charges, crisscross here. All right, so the question here is, though, what's the charge of the Fe? Iron is a multi-charged metal. You can't just look his charge up on the table. All right, this is where you would have to actually get his charge from the other side here. All right, you'd have to look at the FeCl3 and realize that in order to get that formula, you had to crisscross. So this 3 was actually his charge. Okay, so iron is actually 3 plus. Sometimes in these double replacement reactions, you have to get the charge for one of your products from the reactant side. And then OH is a polyatomic, that's just minus. So now when you do your symbols, charges, and then crisscross, we get Fe and then OH3. Make sure you have your parentheses because that's a polyatomic. You're bringing a number down to a polyatomic that's greater than 1. So that polyatomic needs to be in parentheses. Okay, so those are your products that form. Now you just need to balance it. So the first thing I see is I have 3 OHs on the right. So I need there to be a 3 on the left side. Okay, so I have 3 OH now, but now that gives me 3 Na on the left. So put a 3 in front of the NaCl on the right. Well, now that gives me 3 Cl on the right. Well, if you notice, I have 3 Cl on the left. I have 1 Fe on the left and 1 Fe on the right. So if you check everything, everything is balanced here. Okay, so I notice, you notice here that this is not so clean. I wouldn't usually include a lot of this here in my final answers. Like I would, not have any of this stuff. I wouldn't have any of these lines. Okay, so you have to make sure that it's nice and clean. You're just giving the actual reactants and products here that are forming. So this would be your actual final answer. All right, the nice balanced equation with the correct products that are formed. So this is just a quick example of a double replacement reaction. All right, you have 2 clear liquids here, potassium carbonate and barium chloride. All right, when you mix them together, you get a precipitate that forms. All right, you get 2 new compounds. All right, remember we like to leave the metals where they're at, switch the non-metals. But if you're going to be forming ionic compounds here, you're going to have to do symbols, charges, crisscross to get the formulas of your products. So the last type of reaction we're going to do here is a combustion reaction. All right, this is when you have a carbon-hydrogen compound reacting with O2. All right, sometimes this carbon-hydrogen compound has O in it as well, but you just have to recognize that it's some type of usually hydrocarbon or organic here, some CH compound reacting with O2. All right, in a combustion reaction, the beautiful part about this is you don't even have to think about it. Once you know it's combustion, you automatically get CO2 and H2O. Okay, you don't have to, worry about simple charges, crisscross, anything like that. Once you know it's combustion, CO2 and H2O. All right, now those would be the products if the combustion is considered complete. Usually, if there's enough oxygen available, you always get CO2 and H2O. There are versions of this which are called incomplete combustions, where you only get CO and H2O. You only get carbon monoxide and water. Okay, this would have to be something that is told to you. You can't figure out if something's complete or incomplete. So if no information is given for a combustion, you have to assume that it's complete and you get CO2 and H2O. All right. If I expected you to do it incomplete, I'd have to tell you it's incomplete, and then you would know, okay, the products are CO and H2O. All right. So it's kind of important for this one that you don't look at this and say, oh, look, this is a, compound plus an element. And then you think, oh, this is single replacement. This is a specialized version, okay? You have to recognize that you have a carbon-hydrogen compound reacting with O2. And these X's and Y's are here because you could have any number of carbons or hydrogens in the compound, all right? But a carbon-hydrogen compound reacting with O2, all right, forming CO2 and H2O, combustion. These are fun because they're usually the boom reactions, a lot of energy involved. A good example of this is anytime you burn a candle. A candle is a hydrocarbon. You're reacting in the presence of oxygen, and you're forming carbon dioxide and water, and you're giving off heat in the process. All right, so this would be a combustion reaction. So let's jump in and do an example. All right, we have C4H10 reacting with O2. So the first thing you have to recognize is, okay, I have a carbon hydrogen compound reacting with O2. That's going to be combustion here. Okay, so as soon as you know it's combustion, all right, without even thinking, you write CO2 and H2O as the products. All right, in a combustion, predicting the products is the easy part. The harder part about combustions is the balancing. Okay, so there's kind of a trick here to do combustions. All right, in order to balance combustions, all right, here's the trick. All right, first, all right, you always do the carbons first. Okay, so once you do it, know it's combustion, and you predict the products of CO2 and H2O, balance the carbons first. All right, so I can see I have 4 carbons on the left. So now I'll put a 4 in front. That gives me 4 carbon on the right. The second thing you do is your hydrogens. Okay, so I see that I have 10 hydrogens on the left. So on the right now I have 2. So by putting a 5 in front, that gives me 10 hydrogens on the right side. All right, and then the last thing you do is the oxygens and pray. Okay, and the reason why I say that is because sometimes these don't always work out the way you want it to. So now I'm going to look at the oxygen. All right, I see that I have 2 oxygen on the left, but now on the right side, you have to be careful here. By putting these numbers in front, you actually have 2 oxygens in different spots here. So you have oxygens with the CO2 and oxygens with the H2O. So when you put the 4 in front, you now have 8 oxygen here for the CO2. And then when you put the 5 in front, you now have 5 oxygen here. Well, that's 13O. All right, so if you notice, you have O2 on the left side, and there's only O in one spot. Sometimes there's O in the CH compound. There's no other O here. So you need to realize, because it's O2, you could never get an odd number of oxygen on the left side. So as soon as you do this, and you see that you have an odd number of oxygen on the right, and there's no oxygen anywhere else on the left besides the O2, there's a little trick here. Okay, as soon as you see that it's not going to work, you immediately come over to the front of the CH compound, okay, and you put a 2 in front, all right? And then what you do is you double the numbers that you already put there. So for example, I put a 4 in front of the CO2. I'm going to make that one 8, okay? And then I already had a 5 in front of the H2O. I'm going to make that one 10. All right, so put a 2 in front of your CH compound, double the numbers you already had there, retotal up your oxygen, and I guarantee you it will now work. All right, so 8 times 2 for the oxygen and the CO2 is going to be 16, plus 10 from the H2O. That gives me 26. That's an even number. I can get that now on the left side. I can do that by putting a 13 in front of the O2. Now I have 26 oxygens on the left. All right, so that's kind of the way you go about doing these combustions. Do the carbons first, then the hydrogens, and then the oxygens last. Okay, so you just got to be careful with these. Sometimes the numbers get really big, all right, but you can do it if you follow the steps, all right, and pay attention to the rules. So this is a simple example of a combustion reaction. The methane that comes out of the gas jets, the natural gas, reacts with oxygen in the air. All right, it burns, it gives off the heat, and then it forms CO2 and H2O, which you don't even see. They basically go right into the air. But that's a good example of a combustion reaction. So as we've been talking about here, you always need to analyze the reactants in order to determine which type of reaction is going to take place. So when they give you your reactants, look at them, figure out which type of reaction it's going to be. If you see an element reacting with an element, that's going to be a synthesis. There is a rare form of a synthesis where you have a compound reacting with a compound, which forms just one compound, all right? But typically that's not how we're going to see synthesis. If I was giving you something like that, I'd have to show you the product that forms because you would not anticipate that that would be a synthesis. So that's kind of a rare form. Typically for synthesis, it's an element plus an element. If all you see in your reactants is a compound, you know it has to be a decomp and you need to rip it apart. If you see an element plus a compound, that's single replacement. Remember, metals replace metals, non-metals replace non-metals, so you need to analyze the element and figure out if it's a metal or non-metal. And remember, you do need to check the list for a single replacement. Double replacement would be when you have a compound reacting with a compound as your reactant, and then a combustion is a special form where you have a CH compound reacting with O2. So you always need to analyze the reactants to determine the type. Even if it doesn't ask you for the type, analyze the reactants, figure out the type, because that will tell you what products are going to form. All right, so we're just going to look at these reactions here and determine the type of reaction that will form for each. We're not going to predict the products yet or anything like that. Just literally look at them and figure out the type of reaction by analyzing the reactants. So if you want to pause the video, try them, and then see how you did, that's a good idea. All right, so when we look at the first one, all right, always analyze the reactants. So H2 plus O2. H2 is an element. I know it's like a compound, but it's diatomic. It can't be by itself. So that's considered to be an element. O2, same deal. That's considered to be an element. Element plus element is synthesis. Okay, so you know that they would come together and form a compound. All right, next example. I see a CH compound reacting with O2. That's the definition of a combustion. Okay, all right, CH compound reacting with O2. When I look at the third one, Zn. Well, Zn is an element. H2SO4 is a compound. Element plus compound is a single replacement. Okay, remember you would need to check your list to see if it could happen. Zinc is a metal, so we can only possibly kick out the metal in the compound if he's higher on the list. Metals are always written first. So zinc would be trying to kick out the hydrogen here. All right, the next example, H2O. H2O is a compound. So the only thing you have in your reactants is a compound. The only thing you can do is rip apart. That's the definition of a decomp. Whenever you're starting with just a compound, it's a decomposition reaction. All right. The next example here, you have KBr. That's a compound reacting with Cl2. That's treated as an element. That's the definition of a single replacement. Okay. And then the last one, MgOH2 is a compound reacting with H2SO3, which is a compound. That is going to be double replacement. Compound plus compound is double replacement. So you always analyze the reactants, and that will tell you what type of reaction it's going to be. So there's the answers again for the types here for these different reactions. And now what we're going to go through and do is we're going to try a few of these to see if we can go through and predict the products. All right, so we're going to try this example here. We're going to try to predict the products and balance the reaction. This is true chemistry, being able to take reactants, analyze them, figure out the products that form, balance it. All right, this is very important stuff to be able to do because this is what you need to be able to do these larger problems later on in chemistry. The first step you usually got to do is write the reaction. Okay, so you're more than welcome to pause the video, try this one, and then see how you did. All right, so the first thing I notice here when I analyze the reactants, I have a CH compound reacting with O2. All right, that's the definition of combustion. Okay, so without even thinking, I immediately know my products are going to be CO2 and H2O. That's the beautiful part about combustion, is that you immediately know the products are CO2 and H2O. The hardest part here is the balancing. Okay, so like we said before, the way you do the combustion balancing is you start with the carbons first. So I have 3 carbons on the left. All right, so I'm going to make them work. I have 3 now on the right. Then you do the hydrogens. I have 8 hydrogens on the left. So by putting a 4 in front here, all right, that gives me 8 hydrogens on the right. And then the last thing you do are the oxygens. All right, you only have 2 there on the left. It's O2. So you're going to need an even number here on the right in order for this to work, but there's oxygens in 2 spots. So for here, we put a 3 in front of the CO2, so 3 times 2 is going to be 6 oxygen, plus the 4 we put in front of the water. Okay, so that's 4. 6 plus 4 is 10. That's an even number. I can get that. So how can I get that on the left side? Put a 5 in front. That gives me 10 oxygen on the left. Okay, so this would be the complete balanced equation there for this reaction. All right, so here's the next example we're going to try. All right, remember, you always got to analyze the reactants first. So KBr, that's going to be a compound. Cl2, that's an element. Okay, so element plus compound is going to be single replacement. All right, so immediately, as soon as I know it's single replacement, I know I'm going to need to check the activity series. I know I need to analyze the element immediately and figure out if it's a metal or non-metal. So the lone element here is Cl2. Well, that's a nonmetal, okay? So that means if Cl2 is a nonmetal, he could only possibly kick the nonmetal out of the compound. Nonmetals are always written second in the compound. So in order for this to work, the Cl needs to be able to kick out the bromine. All right, because these are nonmetals, you look at your periodic table, you look at the halogens. The only way this works is if the Cl, which is trying to kick out the bromine, is higher on the periodic table than the Br. And if you look at your table, Cl is higher on the table than bromine, so chlorine will kick bromine out. So you immediately know one of your products is going to be your Br that gets kicked out, but it's a diatomic, so it's got to be Br2, okay? Then your other product is going to be the K with the Cl, but remember, it's going to be an ionic compound, so you're going to have to do symbols, charges, crisscross here. So the K is going to join up with the Cl. When you look up the charge of K on your table, it's plus. Cl is in the 1 minus column, so when you crisscross, it actually does end up becoming just KCl. All right, so the chlorine kicked the bromine out, but it's diatomic, and then chlorine jumped in his spot, but I had to do symbols, charges, crisscross in order to form the compound. The last thing I have to do here is balance this. I see 2 bromine on the right, so I'm going to put a 2 in front here on the left, but now I have 2K on the left, so I have 2K on the right, but now that gives me 2Cl on the right, and I have 2Cl on the left, so this is balanced, okay? If you're not able to balance them by going back and forth, you're more than welcome to do the reactants products table, but you don't have to at this point if you don't need to. So the last example we're going to try here, again, you can pause it, try it, see how you do, but we need to always analyze the reactants first. MgOH2 is our compound, okay? H2SO3 is a compound. Compound plus compound is the definition of double replacement. So in your head, you need to be thinking, what does double replacement mean? All right, that means 2 things are going to switch spots. I like to leave the metals where they're at and swap the non-metals here. Okay, so that means I'm going to get 2 new compounds on the product side, but they're going to be compounds, so I need to do symbols, charges, crisscross. Okay, so Mg is going to stay where he's at, and he's going to get a new friend. Okay, remember, his new friend, because he's positive, is going to be the negative part, all right, here from the H2SO3. So his new friend is going to be the SO3. Mg's charge, when you look it up, is 2 plus. SO3's charge here is going to be 2 minus, all right, that's a polyatomic. So when you do symbols, charges, crisscross, they actually cancel. So the first product here is just MgSO3, okay? And then when you get your other product, remember, you're leaving the metal where it's at. So H is going to get a new friend. His new friend is going to be the OH. All right. When you do your symbols, charges, crisscross, H has a plus charge. He's in the 1 plus column. OH is a polyatomic. It's minus. All right. So when you crisscross, just HOH. That's H2O, but you can write it as HOH if it makes your balancing easier, which I think it will here because I have an OH on the left side. Okay, so when I balance this, I see I have two OHs on the left. All right, so by putting a 2 in front here, that gives me two OHs on the right. But now I have two hydrogen on the right. I have two hydrogen already on the left. 1 Mg, 1 Mg, 1SO3, 1SO3. So now it's balanced here. All right, so remember for these double replacement reactions, all right, leave the metals where they're at, swap the nonmetals, but you need to remember to do symbols, charges, crisscross anytime you're forming the ionic compounds in any of these reactions.